Okay, so welcome to my talk. They give me the title of how I won the Dyalog Programming Contest. So the title is very simple and clear why I'm standing here and what I'm going to talk. But this might probably not an APL style expression. So I changed my title to it's like how I interact with APL. It's like this kind of symbols. And I would like this talk to be non-technical and non-academical. So it's just an experience that I share my experience with you guys because I know that many of people sitting in the room that get get touch with APL even before I was born. So it's like, yeah. So about me first. I'm a PhD student from Stony Brook University, and it's in Long Island in New York State. And originally, I came from Shanghai, China, and one of my favorite interests are like I playing musical instruments. It's like piano lover, something. And one interesting thing is that I found when practice pianos and you help your finger to be more agile or something, and it can speed up your typing speed. This is. And I major in computer science at Stony Brook, and I do research in the field of natural language processing with Professor Skinner. And I title myself as an algorithm person. And this is why I started learning programming, not only APL, but other languages like C++, C++, and Java. And as an algorithm person, there is something that is more important than others. It's like the efficiency of the algorithm and also the correctness of the algorithm. So back to the year of 2009, this is the first time I exposed myself very, very little to the APL programming. And if I remember correctly, this is kind of code that I was writing at that time. So don't laugh at me. I know this is ugly. This is some kind of things that a true converting from C++ to APL. But at that time, I will tell you that I feel very happy. Why? Because you changed your language to another different new language, and also you write loops here, and you write a conditional function statement here, and you finish a function here. So believe it or not, if you have finished like this kind of three phases in learning languages, then you will be able to do 80% of the problems. 80% of the problems in very primitive way. So I was happy, but unfortunately, I not going in the wrong way that blocked me from exploring the true power of APL. So this is not the right way. Then let's talk about more APLs. It's like in the year of 2011, so one of my friends introduced me to Dyalog Programming Contest. And at that time, I get myself, get in touch with the book, Mastering Dyalog APL. So I will definitely say that this is an excellent book. And I'll rate it as 5 stars on Amazon if it's possible. And, and this book successfully, tweaked my thought of APL and helped me learn more about APL itself from the scratch. And you know that if you are learning this APL, learning a programming language by your own, and you do not have any teacher, professors that taught you them, then you will have, an idea of how you can program things from, very beginning and from easy to hard and using the symbols and this different kind of things, blah, blah, blah. So it's, very interesting. And what is my thought of APL? So at the first glance at APL, I will find that there's a language construct consists of a bunch of strange symbols. And as a novice or beginner, you'll not be able to recognize what is inside an APL code. But with the experience growing, and you will find that strange symbols in APL is representing very difficult, some different scripts. And these scripts are very powerful. While other people constructing their castle from regular bricks, like in C++, you have to write the loop functions by your own, and you write everything that, from the single variable or something. But APL programmers actually start from a pile that can already be arranged for different uses. which is very good. And programming is easier, and the code is even shorter in this way. And that's one of the reasons that APL is outstanding. But this is not the only reason that APL remains outstanding, because area-oriented thinking is also one other important part in NPL. It's like the thought is all about mathematics, and it originates from mathematics, and it then converted in code. So that's why the operators make operators on work on vectors of input would be very, very useful. And it avoided unnecessary loop expressions, and it helps you keep your code clean and neat logic, and it has more readability for those experienced APL users, but not for those other kind of programmers. So the Polyominoes problems is like a math and computer science section problems, and it is talking about given two polynomials, check if one is some combination of the rotation and the reflections of the others. And for those who have now ideas of what polynomials is, so this is just two-dimensional graph that's connected by multiple unit square, and connect them edge by edge, and so make it like a grid-like but shape. And you can what operations you can do? It's like you can rotate and you can flip the polynomials. So it's like in Tetris, the classical game Tetris, you have the L shape, the block, and you can make like 8 different kind of polynomials from this L-shaped things, using rotating and also reflection. And the second problem of the polynomials is like tell if a 0-1 matrix represents a valid polynomials or not. And the third and the hardest question is to generate all distinct valid N-ominoes. And the core parts of the first question is to detect whether they are the similar polynomials, is to get in all possible polynomials Q, which can be obtained from the original polynomial P, given operations of flip and rotate. So, and this is a very, I think this is a very good expression, the line of code, because what you have in APL is like you have matrix operations, and you can reverse it, you can flip it, and can make use of it and turn it around and see how it looks like. And this kind of things, this line of code, it helps you to do all these kind of combinations like rotate, flip, and you do combine all of them. It's like you have like 2 to the power of 3, it's like 8 choices, and you can make combinations of them. And given the input of the matrix, with this line of code, you can generate 8 different polyominoes. And this is only a line of characters that is 42 characters. Quite impressive, it's like. And what do we have to do next? It's like we have to do regularization. And as you know, if we compare pairwise comparisons to decide whether this one is similar to that one, that will be an n-square algorithm, and it's not effective. Among these possible results, what I need is a regularized shape so that only similar polynomials share the same regularized shape. So it's like for all 8 L-shaped blocks, you have only one that is representative. And what I do is I try to pick one of them with the largest encoding value from Q. That Q is the set we generated according to the original polyominoes. And we just do the encoding value and pick the largest, and from the set, still one line. Quite easy. Now I have from the previous 2 functions, I am able to do regularize the form for any polynomials that is given in the input. And now what I have to do, of course, there are some other steps to finish the whole function. It's like I have to remove the blank lines, columns before rotating. This is also single line. And if you don't do that, you will find that you cannot recognize the L-shaped thing in my hand or L-shaped thing on the ground because the background is different. You have to minimize the effectiveness of the background, and you will find this kind of things are exactly similar. And what we have to do next is to reform and check shape after rotating, because I'm using the encoding function to find the best value. So if the shape of the thing is not exactly the same, that it will cause some confusion in encoding. So with these 4 lines of code, we have successfully solved the first problem of polynomials. Okay, then the next question is about valid polynomial. So this is a question asking whether a matrix P contains valid polynomials, which is by definition connecting unique squares edge by edge and make it a whole connected part. So the idea is to check whether the P contains only one full connected part, then that is valid. Or if it is not, then this is not valid. So what I need is a function find connected parts. So this is my name. And to label all connected parts in the 0, 1 matrix P. After that, the valid judgment can be written as simply in one line. So we find the unique parts of all the labels in connected parts, and I find the size of them. So imagine that if you have only 2 labels which contain 0, which don't contain 0. If it contains 0 and another label, then there's only one connected part. And if it contains only one label, then it is always valid. And it contains 2 labels, not including 0, then this is impossible, because you have a whole matrix, and you have to separate different parts using zeros. So we just need to check the row of the combination of the connected parts, whether they are greater than 3 or not, less than 3 or not. And by doing this, we have to write a function called find connected parts, and the input is given a matrix with each cell is labeled differently, and you do like breadth first search for enough times, and each time you expanded the cell to find the nearest, find the largest labels in its neighbors. And for enough times, you'll find all connected parts sharing the same labels, which is the largest label in the connected parts. And then you can tell that all the cells using the same labels would be in the same connected parts. And this function is quite useful, and I will use it later, probably in the biology problem. And to do breadth first search, so this is simply shift the labels in 4 different directions, then you pick the maximize. So it was like you shifted 1 unit down, you shifted 1 unit up, you shifted 1 unit left, and you shifted 1 unit right. Then you got a cell with all the values of its neighbors, like up, down, left, and right. And then you pick all those values that is the largest, and ignore those originally that was 0, because that 0 means nothing, and you cannot connect a part that's with a label of 0. And after these 2 functions, it's also like 1, 2, 3 lines, and we are all set with the help of the 2 line functions. Then we can do the valid polynomial program. And the final question, and the hardest question, is even more interesting. It's like it allows you to generate N-ominoes, like you have to count them, and you have to generate distinguished N-ominoes, all of them. And this is kind of recursive, like it reminds me of mathematical inductions. Like a valid N-ominoes can be constructed by adding 1 unit block to an n-1 omino. And there's an initial state that n is equal to 0, and you add 1 to it, and you've got a unit square. So here's the logic, and you try to add 1 block, the function, multiple times, enough times, and it should be n times, to the empty cell. It's like 0, 0, row 0. So this kind of things. And then you will be able to get all the polyominoes with exactly n units inside it. So what to do with add one block? So the basic idea is you try to get a function, get a matrix of the blocks, and then you try to add a block to all the possible positions in it, and you see whether this still remains a valid one or not. After that, you pick all those valid ones, and you discard all invalid ones. And so here's a very small illustration. So it's like given a small L-shaped thing which contains 3 unique squares, and you find all the possible extension positions that could be. So it's like you have to give an extra cell around it, and all the cells in this 4 multiplied by 4 square is available. And then you'll go through like a recursive functions, go through all these possible units, and try to add a block on it and see whether it helps you with a new valid n plus 1 omino. And finally, for this example, you will get like 7 different kind of shapes that is some valid polyominoes. It's like the L shape and the Z shape, the square shape, the T shape. So this is the way Tetris is constructed. But we missed the rod one. And this is because you cannot create the rod one by adding one block to this L-shaped things. In order to create the other ones, you have to start it from another initial position, which is small rod consists of 3 squares. And remember that we have the regularization function, and we also have the valid polynomial functions. So that's when we apply these 2 functions to the 7 result here, we will get an L-shaped, the 2 L-shaped overlap with each other, they're similar. And the 2 Z-shaped thing is also similar. 2 T-shaped thing is also similar. And finally, we have 1 square block that is isolated. And you will have 4 unique answers according to using this kind of using this function of adding 1 block. So this is the code. It's like you started from P, the input matrix, and you give them extra surrounding cells by applying 0 to it. And then you pick up the temp variable. Yeah.
Can you be sure, starting with the tree, the particular tree you had, that you'll generate all the possible force?
Yeah. So this is if you generate all the possible. Yes. Yeah, not just one.
Yeah, okay.
This is true. So this is a function that you started from a single polynomial, and what can you generate?
Okay, so you cascade.
Yeah, and I will cascade,
okay.
Recursively from the previous result. When we got all the sets of 3 polynomials, then I can generate using this kind of code, apply them on all this kind of 3 polynomials, and get all 4 polynomials. Tetris, like. And finally, we just need to calculate some validation steps, like I have to count whether a block is put on the existing block. So it's like if you add up a block and it does not give you an extra block, it's still constructed as 3 polynomials, then this is invalid. And also you have to use the previous valid polynomial functions. If you generate another, that is not connected to the original polynomials, this is also invalid. And to distinguish from similar parts using rotations or reflections, then you have to do regularize. And all these kind of things, I think it's less than 15 or 12 lines of code in APL. And I solve all these kind of 3 questions. I think you cannot imagine that in C++ and Java, right? This is definitely impressive. But, So from the solving the problems in math and computer science sections, I have experienced like the awesome script functions, though I have experimented before. But this is also the same kind of feelings. Like the script is very, very powerful and awesome. And you can try combinations of like single character script and script, then it can finish like 80% of the job without using other kind of user-defined functions. This is pretty cool. And then
I just wanted to point out that your solution for generate all the polyominoes was the second fastest of all submitted. It was
Wow.
very impressive.
So there's still the first one, right? so it means that I have a lot of things that still need to learn. It's like I'm not always the question.
Yeah, so I couldn't help but notice the exec
What?
in your code, the execute.
Execute?
Yeah, the eval in your rotations a while back.
Yes.
And so traditionally coming
It's
from
here?
traditionally I almost just forget that character ever existed.
Mm-hmm.
But I see here I can't think of a better way to do this. So do you think that the execute sort of was, did you go for that right away, or did you try to go for some other stuff first?
Oh yeah, I tried some other stuff, and I think this is the most clean way of generating it. Because people know that when you try to do reflections and rotatings, what you have to do is to apply these kind of 3 symbols in matrix, right? But there's different ways that you write the code. I mean, using the execution things that can help generate this kind of things much
I
clearer.
think in this case you could have used the power operator on each one of those functions and avoided the use of execute.
Okay.
But we need power to apply to an array of functions, I guess.
Yeah. So I learned something. See? So thank you. And here's one important experience while I'm learning APL. It's like the dimension is always very important. And I consider this to be a very, very important part in programming APL. And previously, I have no idea of what display function is using, or I seldom use it, so I hardly use them, But the display function for beginners, that will give you an idea of how the matrix is shaping, so how it looks like. As we know that the 3-dimensional matrix may have the same expressive power as the 2-dimensional matrix with each cell containing a 1-dimensional vector. So they have exactly the same kind of dimension, but they are not similar in APL. And when you try to learn using for each operators and when you try to use nested arrays, it is very important that you have the clear mind what the shape of the variable is and what you're gonna do with them. Otherwise, you'll get a lot of error informations. But is that enough? So according to the context rules, so I'm a CS student and I finished the CS sections. But I have to tell you the truth that at that time, nothing can stop me from picking what is inside in engineering sections. Because I would really believe that engineering section and the biology section contains different styles of problems that are also interesting. And plus, I have only write 12 lines of code. That is not enough for a programmer, right? And you feel like I'm getting really getting addicted to APL, and I want to write more code. So that's the status. Okay, let's go to the duck test. So the duck test is something that is used on the Raspberry Pi according to the Raspberry Pi camera, according to the descriptions. And when you have finished this kind of code in a contest, and you can use them to detect some kind of things, and I think this is possible, but I don't have a chance to try it. And the tactics is all about engineering, so it's like some difficult algorithms in it, but it's all about dealing with floating numbers and dealing with this matrix and calculating. So the problems like the first one, given the 0, 1 matrix, find the center of the gravity using a specific coordinates. And the second problem is to help the robot with the camera locate the objects on the ground. Otherwise, if your program is wrong, then you'll find some robot is going the wrong way and it hits something, hit obstacles. And finally, we have a real test, which is, according to the cameras, we are able to recognize some objects. In this problem is ducks, and also some fake objects, which is boars. So let's first see. So I think for the first question, find the center of gravities, and I should. And there's no need to apply an illustration because it is very simple simulations. And you just need to know that calculations on x-axis and y-axis are independent. And then what you have to do is you apply the weighted average algorithms to all different kind of coordinates and apply their values, because the values are different from our usually what we use in our coordinate systems. And basically this is one line, I think, if you can say 1.5 or 1.3. And this line is, tell you how you can run this kind of things, find the center of the gravities from a 0-1 matrix. And then it's the second problem. Then that will be kind of practical. I mean, when you see this kind of graphs, you'll know that you are doing a real world thing, right? So here's the illustrations. It's like you have a camera, and the camera is located on the front of the robot, and it is a height. So it's the z-axis, and it's not appear here, but it has a height. And in front of it, you have a screen. So the screen is 8 by 10, and it puts 10 centimeters wide projection screen. And so it's like five centimeters before, or in the front of the camera. And then you have a viewed object, and the optical illustration is like the viewed object can be seen, and it has a projection on the screen. And then go through the screen, it will finally go into the camera. So there is a straight line connecting the projection point on the screen and the projection point on the ground, together with the camera. And according to the data introduced in the problems, and we have the camera, which is located at 0, 0, 10. And the center of the screen is 0, 5, 10. And we also have the screen, which is 8 by 10. So the screen has 4 corners listed as -5, 5, 6, and towards 5, 5, 14. So there's a simple idea of applying these projections, because a point xs, ys in the screen's coordinates can always be converted to a 3-dimensional coordinates in the real world. So it's like xs, ys in screen coordinates will be xs, 5, and 10 plus ys in the 3-dimension coordinates. And by very simple arithmetics, I mean, the projection point on the ground, xg, yg, will follow the following formula. And it's like the true point on the ground for the given reason, given screen system point xy should be like x converted to x multiplied by 10 and then divided by y. And the optical transformation of y should be -50 divided by y. And the problem description also said that you have something called shade. So shading, shadow, something on the ground. So that's why you have to apply a minor adjustment to it, which is finding the minimum part of the matrix. And you apply a minor adjustment to see whether you have covered the shadow areas, so you finally locate the true projection point on the ground. So what we need is, from the first problems, we need to find a center of gravity algorithm, the program, and also we need min-max. I mean, actually, it only needs to find the mean, but for the further use, I extended to min-max because you have to find the height of the duck later in the third problems. And this is the projection functions, and you will need to find is x, y according to this line given the image. So that they basically solve the problem, and you will find it matches with the sample input and output. And what min-max do is used to find the topmost coordinates and the bottommost coordinates that appear to be 1 in the given matrix. And this is quite simple, and you just need to run something that is, union of the all possible ones, and then you apply the coordinates there, and you'll find the topmost and the bottommost coordinates. Okay, those even more interesting things happens. So it's like the ducks and the balls. So this is the third problems in the engineering section. And the target is not only you have to detect the object, but you have to recognize that the object is a duck but not a ball. So it's like, this is a sample image from the problem set, and you will find the duck and the balls are all like connected parts of a yellow group of unit cells, but the ducks have something that is distinguishable from the yellow balls. And as I recognized it, I thought ducks have eyes, but balls don't. So it's like, and the later part of my program is just trying to find out the eyes of the duck, and then you can recognize this is a duck, but not a ball. So this is like the features of ducks and balls, and also talking about difference between ducks and balls. So, given the problem descriptions, you will have find that the yellow cells are represented as 11 in the problem set. So we have used the find connected parts, the function again. And Q is now set to the connection part, the labels of all yellow connected parts. So this would be the labels of a duck or a ball, because we don't have the distinguish function that can tell the difference between duck and balls at this moment. And then I have another connected parts labels, which is calculating all the labels that is not yellow, background. So as you can see, if a duck has an eye, then the eye is totally enclosed in the duck, and it will not get connected to the whole big background, like what we say here, the gray part. But for the other parts, like the balls, they do not have this kind of things. So the next step is quite tricky. It's like I'm going to combine all the parts of the ducks and the background that is not connected to the background, the whole background, big background. So by doing this, the right part of the code telling me that I can find this kind of things that is inside a duck, and I'll know their labels. And then because I'm using the function like omega minus BFSOneStep omega, so the function is like the label is represented as 1 minus the original label. So after that, I have to turn it around, and then I got the label of all the ducks, because balls will be eliminated from this part. And after that, I got all labels of the duck, and I got the labeled yellow part, which might be a duck and a ball, or a ball. So I apply these things, join them together, and I can get labels of all the ducks. And finally, I find all the ducks. So for each of this duck, it will be represented as a matrix. So just as in the first two problems. And then you will be able to estimate the center of the gravity of the duck and the projection point on the ground of the duck using previous given functions. And what's more, the problem also asks that you have to estimate the height of the duck. And the height of the duck is basically the min value of the coordinates in the matrix and also the max value of the coordinates in the matrix. And you have to grab both of them, and that's done. Okay, so this part of engineering sections is, I think, is more practical than the math and computer science things. And this is not just solving an algorithm issue, but it also feels like your program can really do something in real situation. And after that, there is a free ad slot for Mr. Kronberg. So, yeah, so the Raspberry Pi robot. So this is what he wrote in his page, and I think this is quite interesting, and you have to look at it. So, the other thing in the experiments, and I think I'm running out of time, but the broadcasting and overloading of an operator is also important while I'm learning APL. It's like restricted a lot of things on the flexibility if no broadcasting and overloading is allowed, because you have to multiply a matrix with an integer, or you have to multiply something with a matrix. And with this kind of broadcasting and overloading, you can have multiple uses of your symbols and make it even more readable and useful and concise. It's like, and the programs must have to be familiar with the dimensions of the variables so that they can able to find out what kind of broadcasting it's using. And finally, this is a problem in biology sections. So the problem is about predator and the prey simulations. It's like the name is BunnyFox. And what you have to do is you have to simulate one variable recursive function. You have to simulate a two-variable recursive function and predict the trend. And also what you have to do is simulate a matrix recursive function. So it's a matrix. So there's no offense to biologists. I know JT used to be a biologist. But I think this is not the real biologist is doing, but it is quite interesting. Like they have a connection between biologists and APL programmers. Okay, so this problem is quite simple. It's like given a formula, what you have to do is to simulate this formula. And what's interesting is we are asked to use the trap and find the errors in these problems. Otherwise I will not use this kind of code because it looks not APL style, but actually it's APL. This kind of things I think I did not encounter before, like using the trap, because I always believe my program is like can handle this kind of errors, right? But you have to believe, you have to admit that some kind of things, so some cases you have to do this. And also I learned something from this because I have never used the trap before. I mentioned that there's like 3 problems in each section, but actually there are 5 sub-problems in this biology section, but they are separated into 3 sub-problems. It's like, there's another function you have to simulate is the generation X, which is applying next generation for enough times, like you applied it for 8 times, and finally you got it. And this is interesting because I think when I find that the dimension is important in recursive, you have to figure out that each time the recursive format of the input is exactly the same, so that you can apply it as many times as you want. So this is basically apply next generation for a certain number of generations. That's it. And the next question is about spread and prey. They are using the, both the value of both the population of predators and also the population of prey to create an kind of simulation. So you not only have NT, but you also have PT. And also there's a very similar formula of PT. And what you did is you extend your previous simulation next generation function to let it be extendable and dealing with matrices. And I think this is basically what it's doing. And there's another small sub-problems that allow you to ask you to predict the outcome type of the final simulation result. So it is like when you simulate it for enough times, and you will find the number of predators or prey come to a specific shape, and we are allowed to, tell whether each kind of shape, which kind of shape is really happening. So it's like we have the equilibrium, and we have the oscillation, and we have the convergent and divergent version. So I think all the differences between the peak values in this kind of graphs, and if you can find all the peak values and you analyze the trend of the peak values, and you will finally get one of these 4 possible outcome type. So basically this is the code. I first pick all the peak values of prey populations, and then I counted the value of the top peak and the bottom peak called valley, and also the equal peak. And it's like you have to arrange these kind of peak values according to X, Y, Z's, and then you can decide. Okay, the final questions. The question is about bunnies and foxes on an island. So it's not simulating on a single cell, but this time we're simulating on an island map. So it's a matrix. We have to do the simulating on n multiplied by n matrices, where each cell is a dwelling place. And in each round, what we are asked to do is to calculate the Procreate rate for predators and prey in each dwelling place. And then I have to simulate the birth and death of an individual. And then you have to simulate the migration procedure that happens, allow an individual to move from one cell to an adjacent cell. And first, there's some parts that ask us to do the density calculations. We have to use the density to decide the Procreate rate of a program. It's like we have to calculate the total numbers of, the average numbers of individuals in a 7 multiplied by 7 area. So what we do is for a single cell, you have to find the 7 multiplied by 7 around surrounding place, and you add all the values inside it and calculate the average. So this is what I'm doing. I try to calculate the row matrix, and according to the row matrix, I given a encoding procedure so that when I going to do the loop, loop search, I was able to find in each cell what is the cell around it. So I given the x1, y1, x2, y2 as the bottom, the left, and the top, and the right, the section, the coordinates. And then I know that I have to calculate this in this small submatrix to calculate the average. And finally, you just do this for all cells in the matrix. And this is the density function. You apply around function multiple times and find the density matrix. And there is a small simulation part that's given the Procreate and die rate of an individual in percentage and individual number n also. Then you have to simulate the action of each individual and accumulate the number of next generation. So if the individual have a 50% rate, ratio of being killed or something, then in the simulation you will find this, perished or something, and it will never happen in the count in the next generation. So this is basically my code, and I find that I'm quite get addicted to using the execution functions, because in most of probably this is my habit or something, and using the execution functions probably let me feel more logical something. But this is basically the idea that you have to simulate the function life mn for given input m and n. So this is the third line is basically the most important things. You have to get the rate, and you simulate for each individuals, and you get if the individual was still alive or it procreates, then you add a number. Otherwise, you destruct the number, subtract the number, and then you got it. So the Procreate function is given observation values on a single matrix, and given also the probabilities, you have to do this on the whole matrix, because the previous life function is working only on single variables, and then you have to make it work on the matrices. So this is kind of code, and you combine these kind of things to let it extendable to a matrix. Also, migrate functions. So migrate functions is the only interaction between cells. It's like if you have no migrations, each cell will be an individual, so like an isolated dwelling place, and it will not interact with other places, adjacent places. So the problem says we are allowed to, for each individual to migrate to adjacent parts. So it's said that for the corner, if the individual is located on the corner, then you will have only 3 choices, that you can remain at the same place, you can move to the right, or you can move down 1 cell. And for those who are living on the line, then that will be 4 choices. And for those who are living inside, it will be 5 choices. So actually, this is a problem why they call it Bunny and the Fox. So if something can migrate into the sea, then it is a reptile. It's not a bunny or fox. It's like I first generate this kind of migrate ways. I mean the probabilities, how many ways you can do as migrations, and then I write another small function called random pick, which is a util simulation function. Tell you if you are given m individual, each have unevenly distributed choices. What is the number? How many of them made the first choice? So this is quite a simple idea, but when you got this, you will be able to do this random pick to simulate the migrations on all the matrices in each cell. And each time you have to do that, if you have some of the individuals move 1 cell up, then these individuals are subtracted from the other individuals that could make the other choices. And also you will have to lower the probabilities because the probability of moving up has already been simulated. And then you have to simulate in other directions. This piece of code is, contains a lot of repetitions, and I'm not satisfied with this piece of code, and probably someone can tell you whether I can do it better. And after that, the simulation is almost done, and you have to parade simulation the whole island. And the whole island is like you do the densities, and you find the Procreate rates, and you simulate the Procreate, and then you simulate the migrations. Basically, it's done. And the final BunnyFox functions allow you to do enough generations. It's that it's not simulating for 1 generation, and you have to do it for multi-generations. Okay, bio section cleared. So it's like this section is all of simulations. And I have to say that for programmer simulation, it's not bad because it allows you to, get rid of this arithmetical algorithm logics in just the programming. And this might always be the real project thing that a programmer want to do. That's not want to do, but have to do. It's like you have to do a project that's, because you have customers, their ideas and their projects, you have to follow their minds. And this is what programmers do. And lines of code greatly distinguished from the other 2 sections because we are simulating things, but there's not containing, very valuable mathematical thoughts inside it. And I would make a small comment that if the description of this problem is slightly better, then it will be better for everyone else to understand. So I assume that the people in the room, if you haven't read the problem set, and just from my talk, you'll also get missed in what I'm trying to do. It's like, this is just assumption, but okay. So I think this is a very nice experience. First of all, I'm enjoying the contest, and I'm having fun. So this is the main reason that I continue using APL. So from 2009, it's like 4 years of experience. And it's always good to have background varieties. Like this time we have 3 different set of problems, and which contains different background varieties, and some of them are quite open problems, like real problems in different fields. So these are really attractive, but if only we can, make them more suitable for programmers. Because, I know that real biologists never do this kind of things. And also, this is my idea of reading codes, APL code. It's like APL code provides a very direct way of showing your thought. It is like just giving the code of what I have wrote. So probably you can get an idea of how I think of these problems and how I get into solving these problems. But I still feel that there are too much to learn. It's like I only tried less than 70% of the content from the book, the Holy Bible, like the Mastering Dyalog APL. And there's something that I don't have a chance to try, like the migration level things. And there's also something that different APLs will have different ideas of how to solve the problems because they think it in a different way. So if I would be able to open to expose myself to the other APL's APL's code, then I think I would have another growth. It's like, also APL can do even much more than I thought before. So from the programmer's part of view, it's like I'm just doing the contest and trying to solve the problems. But actually, in real world, APL is trying to solve many other, more strong or more difficult problems. And from this conference, I also see that the GUI applications and the kind of file system applications and the other kind of things. Oh, that's not what I have thought before, actually, as a student. Okay, thank you very much, and I think that's all for the. So if you have any questions, so quick questions.
Have you talked with your colleagues in the department in computer science about this? Have you showed them APL, and what responses did you get if you did?
Not yet. Thanks, Jerry. So not yet. Actually, like college students and our university PhDs, they are getting quite, focused on their own research field or their kind of things. So I think it would be better, or it's good to introduce them to APL environment. But I'm not pretty sure whether they will accept it or not. So this is the question. If you can make them accept it, like Aaron said, that would be a good thing, right? Make students love APL, enjoy, and have fun.
Okay, thank you very much.
Thank you.